Hello and welcome to this lecture, that is lecture number 12 of this lecture series on Turbomachinery Aerodynamics. I think in the last several lectures we have had a chance to interact and discuss about several aspects of turbomachine, the thermodynamics associated with turbomachines and particularly related to axial flow compressors. So, in today's lecture and in the next lecture, that would be lecture 13, we are going to discuss about very significant aspect, very important aspect, which sort of limits the whole operation of the whole engine as a whole, and that is to do with the stability of operation of axial compressors. So, we are going to talk about compressor stability and different forms of instability that we see in modern day axial compressors, and what are the effects of instability on the compressor performance and also the performance of the engine as a whole. And so we will of course continue discussion on instability in the next lecture, where we will also be talking about the effect of inflow conditions on the initiation of instabilities, as well as the effect of trying to control instabilities and how we can try and control instabilities in axial compressors, and what are the implications of this control on the performance of the engine as a whole. So, instability is the major topic that we are going to discuss in today's talk. So, basically we are going to talk about two different modes of instability. We will of course be talking about that in great detail, that is to do with rotating stall and surge. So, these are the two basic aspects of instability we will be talking about. Of course, we will cover instability in general as well in today's talk. Now, one of the major issues with the engine operation and the effect of trying to operate under off design conditions is the fact that there is one component which will sort of limit the performance or limit the operation of the whole engine as a whole, and that is the compressor. So, compressor is the component which sort of determines the stability and limits of operation of the engine as a whole. Now, in the last class, if you remember, in one of the last lectures we had discussed about the axial flow compressor performance map. During this discussion, I think I had mentioned that there are two limits of operation of the axial compressor. On the right hand side of the compressor map, we have what is known as this the choking point or the choke limit, which is to do with the maximum mass flow rate, and on the left hand side of the compressor map we have what is known as the surge limit or surge margin, or the limit to which the surge can occur. So, these are the two bands or regions or lines within which the compressor operation is considered stable or feasible. So, if we try to operate the compressor beyond these limits, the compressor is going to go into instability modes and the operation cannot be successfully carried out. And therefore, what we also see is that if you look at the engine as a whole, compressor being one of the major components of the engine, if the compressor enters into an instability mode, obviously that is going to have a detrimental effect on the downstream components like the combustion chamber, therefore, the turbine and nozzle and so on. So, the stability limits of the compressor will kind of limit the operation of the whole engine, and that is why it is very important that we understand what are these different modes of instability and how we can sort of understand the mechanism of these instabilities and see what initiates these instabilities, and of course, in subsequent lectures we will also look at how we can attempt to control these instabilities if at all possible. So, compressor instability or the limits of operation of the engine is limited by the operation or range of operation of the compressor itself. So, let us take a look at some of these salient features. As I mentioned, compressor performance obviously is a key factor in the overall engine performance. At a given rotational speed, we know that the maximum mass flow is determined by the choking, and as mass flow is throttled, there is an eventual breakdown of the stable flow conditions, and the stable performance or range of the engine is therefore dictated by the compressor performance itself. And what we also like to understand here is the fact that an aircraft engine, as we know, is designed to operate for a certain condition which is known as the design condition, but during takeoff to climb and cruise and finally to land, we see that the engine is operating under a variety of operating conditions. So, how is it that we can kind of ensure that this engine is going to operate stably in all these operating conditions? Now, that is a big challenge for an engineer, for an engine designer, because there are so many components that fit into an aircraft engine, and how do we ensure that each of these components will be able to perform well under all these so called off design conditions. And one of the most crucial components amongst all the other components is the compressor, because compressor performance, as I mentioned, is limited between the choke limit and the surge limit, and there is a certain band which we can use for a stable operation of the compressor, and we do not want the compressor to operate at towards these two limits or very close to these limits, because that will risk the compressor in the event of an off design operation, that it might go into the instability modes. Therefore, there is a narrow margin of operation of the compressor which is known as the surge margin. We will discuss that a little later as well. That is the band of operation around the design point, where we can say that the compressor operation is stable and compressor is operating in a fairly high level of efficiency, because that is another important aspect, that you might still be able to operate a compressor at any other given point, but then that would be an operating line where the or operating point where the efficiency is very poor, and so a poor efficiency of the compressor will also affect or impact the overall efficiency of the engine. We do not want, or an engine designer would never want, that the engine is operating in a poor efficiency zone. So, high efficiency is one of the key parameters, and so is the stability of the compressor itself, and surge margin is that margin which engine designer provides or a compressor designer provides, so that the engine can operate in that margin in a stable manner and also with a reasonably high level of efficiency, which is also very crucial for the performance of the engine as a whole. And so, the ability to efficiently operate such an engine at all these operating conditions will also depend upon a successful match of all the components within an engine and also within the stable operating range. So, for example, an engine has, as you are probably aware, and it will typically have an air intake, then a fan or a compressor, then the combustion chamber, turbine and a nozzle. So, these are of course, the salient features of a so called turbojet engine, and so all these components need to operate in a kind of a synergistic manner in the given operating range, as well as under off design conditions which are expected to be encountered by the engine. And the compressor being the key component in all of them, it is very necessary that the engine designer understands the performance of the compressor over a range of these operating conditions. So, what I will do now is to quickly go through the compressor map once again. We have discussed that in one of the earlier lectures. Let us take a quick look at that once again, and we will also try to see or try to understand what I am currently talking about, what are these different limits that I have been talking about. So, here is a typical compressor map, a typical multi-stage compressor map. On the y axis we have the pressure ratio, and x axis is the corrected mass flow rate m dot square root of theta by delta, where this is the temperature ratio and this is the normalized pressure ratio. So, a typical compressor map will consist of these lines which correspond to different speeds. So, rotational speed is given by these different lines, and we have seen two different limits that I was talking about. One is about choking, that is this line here. If you draw a line here, that corresponds to the choking limit, because you can see that here beyond this point the mass flow rate does not change, and that for a particular speed that is the choking limit. On the left hand side, we have a line which I have denoted here as surge line. We will talk about surge in lot more detail in some of the later slides. This is the surge line. Compressor operation on the left hand side of this line is unstable because of occurrence of surge. And what is shown here by the dotted line is the engine operating line. Now, engine operating line is the line which the designer has set for a stable operation of the engine at different speeds, and the difference between this and the surge line is the surge margin. So, you can see that it is a rather narrow margin, it's been slightly exaggerated here. In modern engines, the surge margin is kept very narrow because the higher efficiency is obtained very close to surge, and so surge margin is this difference that you see here. So, this is a typical compressor map, and this is going to limit the performance of an engine as a whole, because you have so many components, other components in an engine, the turbine, the combustion chamber, the nozzle intake and so on. And so, compressor map will tell us what is the kind of limit that we have for operating this engine in a stable manner. So, in the operating line that you saw, that is basically corresponding to the line or zone which has been designed by an engineer for a stable operation of the engine. The engine is still allowed to deviate from this operating line by a certain amount, but certainly not beyond the surge margin, because that would mean that the compressor has surged, and that would also mean that the engine operation is in danger. So, we will discuss about surge a little later. So, the basic intent of this lecture is to understand what are these different instability modes that are likely to be encountered by a compressor, and what is the mechanism of these instabilities and what happens really during these instabilities. But before that, let us first try to understand what we mean by an instability in the first place. Let us try to understand let us try to define instability, and from there we will talk about instability as applied to a compressor. Now, if you have undergone certain courses in physics and equilibrium and so on, you probably are familiar with stability or instability as a general term. So, we are referring to that in this context also in that fashion. Basically, what we refer to as stability of a compressor is the fact that if a compressor or if a system is perturbed or disturbed from its equilibrium position, if the perturbation or disturbance is removed and the system returns to its initial or original state, then we refer to this system to be a stable system. That is exactly what we talk about when we talk about a compressor as well, that if the compressor operation is perturbed by some downstream condition like a throttling of the nozzle or something like that, then if that perturbation of course, that will lead to certain change in compressor operation. Now, once that perturbation is removed, if the compressor returns to its original state, then we say that the compressor operation is stable. And if it does not return to its original state, and if the compressor operation enters into an entirely different mode with all kinds of problems, then we refer to this state of operation as an unstable or unstable mode of operation of the compressor. We refer to this operation as that instability has set into this compressor operation. So, stability in this context of a compressor is basically related to the response of a compressor to a disturbance which perturbs the compressor operation from a steady operating point. And if the disturbance is transient, the performance will be considered stable if the system returns to its original state of equilibrium. If the response is to drive the operation away from the operating or original point, then the operation or performance is unstable. So, the compressor could, depending upon its mode, it could operate in either of these regimes. It could either return to its original state, where we say that the compressor is indeed stable, or it could also happen that the compressor does not return to its original state, and that is referred to an unstable mode of operation of the compressor. So, these are the different issues that we are going to discuss in today's talk what are these unstable or modes of instabilities that a compressor is likely to encounter. So, let us now talk about the different types of instabilities that a compressor will encounter. We can classify instabilities encountered by a compressor broadly into two types. One is known as an operational instability and the other is known as aerodynamic instability. So, there are two areas of compressor performance that relate to stability. Basically, one is to do with operational stability, other is aerodynamic stability. Now, operational stability involves matching the performance characteristics of the compressor with the downstream components. Aerodynamic stability is the limitation of steady operation of the compressor due to what are known as surge and stall. So, we will spend a lot of time discussing about the aerodynamic stability, because this course is primarily dedicated to aerodynamics of compressors and turbines and other turbo machines. So, but let us also try to understand operational stability as well. Now, operational stability, as we have just seen, relates the compressor to certain downstream components as well. That is, if the downstream components kind of perturb the compressor operation, what happens to the overall operation of the compressor and so on. So, that mode of stability is basically referred to as the operational stability. And here we consider not just the compressor, we consider components which are also kind of dependent on the compressor, or components which kind of influence the compressor performance as well. And what are these different components? It could be downstream components like the combustion chamber, the turbine, the nozzle and so on. So, these are the components which can kind of influence the compressor performance. So, operational stability will also take into account all these components put together and their effect on the compressor performance. So, in operational stability, the complete compressor system, including the inlet ducts, guide vanes, the rotor stators of the compressor and the exhaust systems are considered. And operational stability basically depends upon the rate of change of pressure rise or pressure drop as the mass flow rate varies. System stability is established when the rate of change of compressor pressure rise with mass flow is algebraically less than the rate of change of throttle pressure drop with mass flow. Well, the last statement looks a little confusing. I'll try to explain that in one of the next slides, which I'll talk about, where I'll try to explain what I mean by this last statement, saying that the stability is established when the rate of change of compressor pressure rise with mass flow is algebraically greater than the sum of the less than the sum of that of the throttle mass flow. So, let us try to understand this in little more detail. Now, for that we will again take a look at a compressor map, a very schematic of a typical compressor map. We will try to look at what we mean by this particular statement and how we can analyze operational stability of a compressor. So, I have here a typical line, operating line of the compressor speed line. What is denoted here by the solid line refers to the compressor operation, and what is denoted here by the dotted line refers to the characteristics of a throttling device or a flow device. It could be a nozzle or it could be some other component which is downstream of a compressor and that can change the compressor operation. So, solid line refers to the compressor operation, this line refers to a throttling operation. So, there are three different modes of operation I have shown here. Let us take a look at the first one. Here we have the compressor characteristic shown by this line and the throttling characteristic shown by this. So, the throttling characteristic intersects the compressor characteristics at this point, which is denoted here. Now, according to what we had discussed in the last class as well as in the earlier slides, this line which is shown here should be a stable operating line. Any point here should be stable and any point to the left of this should be unstable. Let us take a look at why that is true. So, if you look at this line of point of intersection here, that is lying on a region where the compressor compressor map has a negative slope. Now, when the slope is negative, it means that as the throttling device is operated, let us say you increase the throttling pressure, with an increase in throttling pressure, it leads to, or with an increase in throttle basically means that the mass flow is reduced. So, as the mass flow is reduced, what happens here is that there is a corresponding increase in the pressure rise across the compressor, and therefore, that corresponds to a region where the operation should be stable, because you are throttling it, the pressure is increasing, and therefore, that is what exactly should be happening. Now, let us take a look at the second plot here, the second one shown here, where the throttling characteristic intersects the compressor line on this curve here on the left hand side of the surge line, and that is the intersection point here. So, here what we see is that the slope of the throttling line is less than the slope of the compressor line, compressor operation. So, compressor characteristic has a steeper slope than the throttling characteristic. So, this means that since the slopes are different here, the rate, let us say we consider the rate of change of throttling mass flow, rate of change of throttle, and we compare that with the rate of change of compressor characteristics. So, as your throttling characteristics are changed, rate of change of that is now less than the rate of change of the pressure drop across the compressor, which means that as you throttle more and more, the pressure drop across the compressor is less than what it should have been. And therefore, what will happen is, since the pressure drop is low, it will lead to a scenario where since the throttling mass flow rate of change of throttle mass flow is larger, it will lead to further decrease in mass flow, and so on there. And again, since the slope of the compressor is still higher, it could lead to further decrease in pressure ratio, and this goes back and forth. So, you can clearly see here that if the throttling characteristics has a slope which is less than that of the compressor characteristic, then that is a region where the compressor operation is going into an unstable mode of operation. So, this is a typical example of an operational instability. Now, the other extreme of this is something that is theoretically possible, but we will see that aerodynamically that is something that cannot be really achieved. That is the third characteristic that we have here, where the compressor characteristic has a slope which is less than that of the throttle characteristic. So, there is a difference in the slope between the compressor and the throttle, and what causes that? I mean, what happens in such a scenario? So, if the throttle line has a slope which is greater than the compressor slope itself, what it means is that as you increase the rate of change of, or as the rate of change of throttle is varied, the corresponding pressure ratio or drop in pressure ratio is lower than that of the corresponding rate of change of mass flow. And therefore, what happens is, as the mass flow is changed here, since that rate is higher than the rate of change of pressure drop, then it means that the pressure drop does not fall at the same rate as that of the mass flow, and therefore, this could lead to us, at least theoretically could lead to a stable operation of the compressor, which means that we are not really in an unstable mode here, even though we are operating on the left hand side of this line, which is theoretically supposed to be an unstable zone of operation. But what we see is that it is in fact theoretically possible that we can still operate, we can still have an operational stability even while operating on the left hand side of the performance curve. And so, theoretically it should be possible for us to operate on that side, but what we will see next is that that is the region where aerodynamic stability cannot be achieved, and that is what the next topic that we are going to talk about, that is to do with aerodynamic stability of an axial compressor. And that is something of little more significance to us, because we are talking about aerodynamics of compressors right now, and so understanding aerodynamic stability probably would be of a little more significance to us. So, what do we mean by aerodynamic stability? Now, aerodynamic stability basically refers to the compressor system and its ability to maintain or deliver a higher or increase in pressure rise even when there is a perturbation in the mass flow to a lower value. That is, as you perturb the mass flow to a lower mass flow, ability of the compression system to either maintain the pressure itself or increase the pressure for a lower mass flow, which is what happens if you remember on a compressor curve. As you keep going from the choke limit to the peak pressure, as you decrease mass flow, you are actually getting a better higher and higher pressure ratio up to the peak pressure point where the slope is kind of 0, and beyond that to the left hand side is where a drop in pressure, drop in mass flow will also lead to corresponding drop in pressure ratio, which is not obviously a desirable characteristic because it leads to aerodynamic instability. So, this part of the compressor characteristic which has a positive slope is a region containing subsystem stall or complete instability, which could lead to surge. So, stall and surge are those two instabilities which will get initiated if you were to operate on the left hand side of the curve. So, in this region, as we have already seen, operational stability may still be possible, but aerodynamic stability is not possible. So, let me explain that little better. So, this is a typical compressor characteristics because it is a rather flat curve as compared to what actually happens in compressors where you could have a sudden drop in certain conditions. Now, here the dotted lines indicate throttling characteristics, as we have seen in the last picture as well. There are three different characteristics shown here given by A, B and C. These are three different throttling characteristics, and the solid line corresponds to the compressor characteristic itself. So, between points A and B, or between these lines, throttling characteristics of A and B, as we have seen, these characteristics intersect the compressor characteristics where the slope of the compressor performance is negative. Therefore, these lines correspond to stable operation of the compressor itself. Now, here what we have is that let us consider, let us say, point A. Now, here we have an increase between point A and B, increase in the energy input would always be greater than the corresponding increase in losses in the compressor, and therefore, you continue to get a higher and higher efficiency. At point B and beyond that, higher the input energy, the losses encountered by the compressor is higher than the input energy itself, which means that we are beginning to lose efficiency beyond this point B. So, beyond operating point of B, we kind of start losing efficiency, and beyond point C, the loss in efficiency becomes so high that the compressor operation itself is unstable because of the initiation of aerodynamic instabilities like stall or surge. So, between these points or lines A and B, where we could operate the compressor in a stable manner, but you would like to operate it as high an efficiency as possible, which is where which is probably close to the point B, where the rate of energy input continues to be much higher than the rate of losses or increase in losses. Beyond point B, the losses kind of start building up, and then energy input and the losses kind of, there is a huge mismatch between that, you begin to lose efficiency there. So, as we have seen, it is still possible to operate on the negative slope of the compressor map, but that is only an operational stability from the operational stability point of view, but that is the region where the compressor operation is aerodynamically unstable, and you obviously cannot operate in that region where compressor is aerodynamically unstable. So, let us now start discussing about, see, we have been talking about instabilities in great detail and what is meant by instability, like operational instability and the aerodynamic instability. Let us discuss about the aerodynamic instability in little more detail. Now, I think I mentioned in the last class that when we are talking about multi-stage compressor characteristics, that there are primarily two modes of instabilities that a compressor can encounter. One is to do with stall and the other is to do with surge. Now, we will first take up stall and understand stall in little more detail before we move on to surge. So, stall and surge are those two instability modes, surge being the extreme instability, and stall is probably a precursor to surge in some sense. So, let us take up stall first, and what we mean by stall and what are the different types of stall that a compressor can encounter. So, stall basically can be attributed to, if you have undergone a basic aerodynamics course, if you have looked at flow past an airfoil, as you increase the angle of attack of an airfoil beyond a certain angle, you know that the airfoil will stall. So, in the compressor also we encounter a phenomenon which is in some way similar to what you have learned in the CL versus alpha curve, for example, that beyond a certain alpha or angle of attack, the airfoil stalls. So, if you look at it from a very simple perspective, compressor stall also in some sense originates or begins from kind of an airfoil stall itself. Now, there are two types of stall that we can associate with a compressor operation. One is to do with individual blade stall and the other is known as rotating stall. Now, individual blade stall occurs when the entire blade row would stall at once, and this is something that one would encounter or see if you look at, let us say, an airfoil or a set of an airfoils like in cascade. We have already discussed about cascade, and while carrying out, let us say, a cascade experiment, since all the airfoils are at the same stagger, and as you change the incidence of all the blades change simultaneously, and so if there is stall encountered on one of the blades, it should be the case that all the blades have stalled simultaneously, because all of them have the same stagger and the incidence angles. So, since all these airfoils are identical like in a cascade, all of these blades are likely to stall, and that is basically referring to an individual blade stall. Well, but in an actual compressor, we do not really have a scenario where all the blades are because it is in a cylindrical coordinate sense, and unlike a cascade, a linear cascade where they are all arranged in a linear fashion. In actual compressor, one is likely to encounter what is known as a rotating stall, and we will discuss about rotating stall in a little more detail and what is meant by rotating stall. So, rotating stall is the most common type of stall that one would encounter in an axial compressor. Rotating stall would basically involve progression around the blade annulus of a stall pattern, in which one or more adjacent blade passages are instantaneously stalled and then cleared for unstalled flow as the stall cell progresses. That is, in rotating stall, one would have alternate stalling and unstalling of either one blade or a group of blades. That is, there would be a certain stall cell which would continuously move along the annulus. This is because the rotor itself has a rotation, and therefore, the stall cell continuously moves, which is why it is known as rotating stall. So, either one or a group of adjacent blades would be stalling, and this stall cell progressively moves along the annulus of the compressor itself. Let us try to understand what is the mechanism of rotating stall and how it propagates. Now, let us consider a set of blades of a typical axial compressor that you see here. So, let us assume for the moment that due to some reason, it could be because of the incoming flow being non-uniform or because of some local issues with the stagger of one of these blades or set of these blades, that the incidence angle to one of these blades exceeds the design value, leading to stalling of the blades. As you know that if this is, you can kind of compare this with an airfoil characteristic, CL alpha characteristic. As you keep increasing alpha beyond a certain angle, the flow stalls. So, something similar can be visualized here as well, that the incoming flow to, let us say, either one blade or a set of blades has a higher incidence than what it should have been, leading to separation from one of the surfaces of the blade, leading to stall. So, what you see here is basically a stall cell, what we refer to as a stall cell. Now, this increased incidence and resulting in a stall of this blade basically causes the flow to enter the adjacent blade also with a higher incidence, but at the same time it unloads the preceding blade. And since these blades are also moving, so the blades have a rotational direction in this direction. So, as these blades move, and since the incidence continuously changes from one blade to another, what happens is the adjacent blade now sees a flow with a higher incidence than what it should have been, which means that this blade will now begin to stall, and as this adjacent blade stalls, what happens is that now this blade has undergone stall, and because of this stall which this blade has undergone, what basically happens is that this would unstall the previous blade which was earlier undergoing stall. This is owing to the fact that these blades are now are also rotating with the rotor speed. Now, so as these blades rotate, this blade which was earlier undergoing stall will now unstall, and the stall now progresses to the next blade, and this continues. And therefore, what you see is that effectively one can see that the stall cell is now moving in a direction which is opposite to that of the rotor rotation itself. So, rotating stall usually has a direction of propagation in a direction opposite to that of the rotor. So, here we have visualized one blade which is undergoing stall. It is possible that there could be multiple blades which are undergoing stall, and you may have multiple stall cells in fact propagating along the annulus of the compressor. We will also see some of these examples in some of the later slides. So, this is a typical mechanism by which rotating stall occurs. In fact, in the next lecture that we will discuss, basically we will be attributing rotating stall to the effects to do with the incoming flow itself. That is, if the incoming flow is non-uniform or what we refer to as a distorted inflow, that has an effect in initiating rotating stall in axial compressors. So, as I mentioned, you could also have more than one set of stalls or stall cells moving along the annulus. Like you see here in this example, you have multiple stall cells which are propagating along the tip of the compressor blade. So, you could have multiple number of stall cells. You could have either one stall cell or you could have number of stall cells, and in fact, it has been observed that there are as high as 9 stall cells which have been observed experimentally. So, between 1 to 9 or more stall cells are possible, and so what we will also see is that these number of stall cells also tell us something about the nature of stall themselves. That is, either one could have a mildly progressing stall, or one could have what is known as an abrupt stall. And so, we will also see what are these two different types of rotating stall initiation mechanisms that are possible. Now, it has also been observed that rotating stall, if allowed to progress and continue, will lead to another instability or an extreme instability of operation of the compressor, which is known as surge. We will discuss surge in little detail later on. The rotating stall often precedes surge, and we have seen that the rotating stall propagates in a direction opposite to that of the rotor rotation, and you could have rotating stall frequency as high as 50% of the rotor frequency itself. You could also have stall in different types. You could have what is known as part span stall. That is, if you consider this to be the annulus of the compressor, this being the hub and this being the tip of the compressor, you could have stall which is extending only up to a part of the span. It is not extending from the tip all the way to the hub, but there are multiple stall cells as you see here. Or you could have full span stall, as you can see here, stall cell is extending all the way from the tip to the hub. Or you could have the entire annulus itself which has stalled, which is what would happen if we approach or enter into surge, which is why I mentioned that rotating stall often precedes surge. Now, rotating stall can, as I mentioned, be initiated by a variety of reasons, the most common being off design operation, and the other common reason for initiation of rotating stall is inflow distortion. That is, if the incoming flow to the compressor itself is non-uniform, there could be small pockets or regions where the local flow incidence approaching the compressor rotor would be much higher than the design incidence, leading to initiation of stall in some of those blades. And once initiated, it will begin to propagate, and if conditions are favorable, then the stall propagation is continues and it develops further, and in some cases it can also be dissipated if the conditions are not really favorable. The other reason for rotating stall initiation could be a slight mismatch in some of the blades having slightly higher stagger or a slightly different profile due to certain manufacturing defect and so on. So, once this kind of a compressor enters into certain slightly off design condition, it is possible that these blades which have a slight mismatch in stagger or profile will initiate rotating stall. And I have also mentioned that the number of stall cells can be as high as 9 in certain cases which have been observed, or as low as 1, and number of these stall cells is also associated with the type of stall. So, there are two types of stall which have been observed experimentally. One is known as progressive stall and the other is known as abrupt stall, and some of the latest literature refer to these modes of stall as the modal inception of stall or spike initiated stall. That is, if in some cases a stall is initiated in a progressive manner, in a mild manner, it is basically also referred to as modal inception of stall. Or you could have an abrupt or sudden initiation of stall, it is also referred to as spike initiated stall. Now, in progressive stall we have a gradual reduction in total pressure ratio after initiation of stall, whereas in abrupt stall there is a discrete jump or decrease in the pressure ratio as stall is initiated. Now, progressive stall is usually associated with multiple stall cells. We could have more number of stall cells, which is why one would have a progressively decreasing pressure ratio. And in an abrupt stall, it has been observed that it is initiated with one stall cell, but that is a larger stall cell extending all the way from the hub to tip. So, progressive stall or modal stall inception usually is associated with multiple stall cells which are propagating. Abrupt stall or spike initiated stall is usually associated with a single stall cell which initiates this kind of a stall. So, if you look at characteristics, compressor characteristics, where we can try to understand these two modes of stall. On the graph that you see here on the left hand side, we have pressurized versus flow. The compressor characteristic operating all the way from choke with decrease in mass flow or as we throttle the compressor, leading to higher and higher pressure ratio, peak pressure ratio, and then the pressure ratio begins to drop. So, this is a typical progressive or modal stall inception, whereas on the right hand side what you see here is that the compressor characteristic continues to increase up to the peak pressure, and then there is a discrete jump or drop in pressure ratio and the compressor enters into stall. So, this is a typical spike initiated stall or abrupt stall which has been encountered by this kind of a compressor. So, these are two different modes of compressor stall which have been observed by different researchers, and they attribute of course, there are a lot of mechanisms and theories which have been kind of proposed on why this kind of stall mechanism is initiated and so on, which I guess will not go into details of that. So, let us say for example, we consider just the progressive stall. Let us try to look at what really happens when progressive stall is initiated. So, this chart here basically shows us variation of stall pattern in a typical progressive stall. Well, not necessarily true for all the cases, but in this particular case what has been observed is how progressive stall kind of can be explained by using these characteristics. So, let us say stall has been initiated as you increase as you throttle the mass flow, we have an increase in pressure ratio, we reach the peak pressure point, and since this is a progressive stall, we have a gradual decrease in the pressure rise characteristics. So, what really happens in this scenario, that just to mention here, in most of the compressors that we encounter, stall is initiated from the tip of the blade. So, which is basically referred to as a tip critical rotor, or stall is initiated from the tip of the rotor, which is true for most of the compressors. Of course, there are exceptions also where stall could also be initiated from the hub, but those are relatively rare. So, as you enter into the negative slope of the compressor characteristic, we have stall being initiated from the tip, and as we progress further down, we have part span stall, we have multiple stall cells, and then this extends to full span stall, and then of course, we go into deep stall where the whole large fraction of the annulus has stalled flow. So, this is typically how a progressive stall would evolve and develop. Okay, so, having understood about rotating stall, let us now quickly look at the other mode of instability, which is probably a more serious mode of instability, that is surge. Now, I mentioned of course, that it is possible that when we enter into deep stall, full annulus is under stall, we could also lead this obviously could also lead to surge. Now, what happens in surge is a complete breakdown of stable operation of the compressor flow, and there is a violent oscillation of mass flow back and forth along the length of the compressor. So, this is typical of a multi-stage axial compressor. What basically happens is that as you are operating on the left hand side of the compressor characteristic, any decrease in mass flow rate will be accompanied by a corresponding or greater decrease in the pressure ratio, and therefore, there is a drop in pressure ratio which may not be matching with the pressure ratio downstream, and so that leads to a backflow from the downstream all the way to the upstream of the compressor, and so this kind of mass flow fluctuates back and forth in the compressor, and as you can visualize, this is a complete breakdown of the mass flow and leads to failure of the compressor operation itself, which eventually obviously also leads to failure of the engine, could lead to engine shutdown and so on. So, that this is a very extreme case of instability of the compressor, which obviously is something that all designers would want to prevent, and which is why I have been mentioning about surge margin, which is provided in all axial compressor operation, that this is the band in which the compressor is stable, and one should not exceed the surge margin, because the compressor is likely to encounter surge. Now, surge is basically characterized by fluctuations in the average flow throughout the compressor, and in this case the net flow through the compressor can either be positive or negative, and it is highly transient phenomenon. And this is different from a rotating stall, wherein there is still an average flow which is passing through the compressor and is constant with time. But during surge, the system obviously is unable to attain a stable match with a throttle which is downstream. Now, in the compressor operating line, we have seen the surge line, which basically denotes the locus of unstable operation of the compressor, and surge obviously may lead to flame blowout in the combustion chamber and can obviously lead to substantial damage of the compressor itself. So, during a design of a compressor, there is a certain margin which has been provided by the designer, wherein one is recommended to operate the compressor, which is known as the operating line, and there is a difference between the operating line to the surge line. So, that is basically the surge margin, that is the margin which has been provided for operating this compressor. That is, even under off design conditions, one should ensure that the off design operating point is still away from the surge line, and it is not very close to the surge line, because if it is too close to the surge line, there is always a risk that the compressor might get pushed into surge, which is obviously detrimental, as we have seen. So, if you look at this compressor map, which I had shown earlier as well, this is the surge line, it is the locus of all the surge points. If you join the surge point at different operating speeds, then we get what is known as the surge line, and this dotted line is the engine operating line, and so this difference is basically referred to as the surge margin. And modern day compressors are designed to operate with a very small or narrow surge margin of and that is basically to ensure that the compressor is operating with a fairly high efficiency, delivering a high level of pressure ratio. At the same time, we would also want to ensure that the compressor does not move very close to the surge line, because obviously that is quite risky. So, let us now look at some of these examples of actual experiments which have been carried out several years ago. This is one classical example of characteristics, single stage characteristic, as it is shown here. It is from a very old paper by Hubert in 1952. As you can see, it is more than 50 years old, but this is still considered to be a classical paper, because it explains a lot of the issues related to surge. So, here you can see it is a compressor operation at two different speeds, and what you can see is also what I have referred to as hysteresis. I will probably explain this in little more detail in the next class, but what you see here is as the compressor enters into surge between points A to B, this, as you can see, there is a sudden drop in the performance characteristic, and as you try to recover the compressor operation from its surge line or surge point back to stable operating range, it does not trace the same path. And this loop, as you see here, is basically referred to as hysteresis. You might be familiar with hysteresis of magnetic materials, paramagnetic materials. So, this is a similar aspect which is observed in compressors as well, as the compressor enters into surge or deep stall, and if you recover from the surge or deep stall operation, the operating points are slightly different, and that is attributed to hysteresis. I will explain that in more detail in the next class. Now, there is one more example that I would like to show here. This is from again an old paper by Wright Sir and his group at MIT, and so this is also explaining the hysteresis and associated with surge and its initiation. So, as the compressor operation is taken from its choke point all the way to peak pressure, and you can see there is an abrupt stall and surge operating, or the compressor basically enters into a surge mode of operation, and once it is taken out of that mode of operation, it takes a different path, and that is basically attributed, as I mentioned, to hysteresis. So, that is also seen in this particular characteristic, as you can see. Now, what Wright Sir also observed in his experiments was the effect of rotating stall and surge, and you can see how these instabilities were actually measured in terms of velocity variation. So, if you were to measure variation of velocity in a compressor which is, let us say, undergoing rotating stall, one would see fluctuations, as you can see, several fluctuations within a second, which means that the frequency of rotating stall is several magnitudes higher than that of surge. You can see this in surge, 1 second has probably just one or few fluctuations, whereas in rotating stall you have several fluctuations taking place in a second. So, the frequency of rotating stall is usually at least one order magnitude higher than that of surge, and in surge you can see the fluctuations which are basically axisymmetric, and the flow basically moves back and forth with a frequency which is much less than that of rotating stall. As I mentioned, rotating stall can have frequencies as high as 50% of the rotor frequency itself, and which means that rotating stall can indeed have very high frequencies. Surge, on the other hand, is not related to the rotor frequency. It is just axisymmetric motion of flow back and forth in the compressor, which could have very low frequencies, usually one order less than what is encountered in rotating stall. So, this is just to summarize the different modes of instabilities what we have discussed in today's lecture. Of course, there are a few more aspects that need to be discussed, and I guess I will take that up in the next class, where I will also talk about what I mentioned in the last slide about hysteresis and so on, and we will obviously discuss lot more details of instabilities and inflow conditions on instabilities later on. So, in today's lecture basically we discussed about instability in general and instability as applied to compressors and what we mean by instability of axial compressors. You have seen there are two modes of instabilities in general, the operational instability and the aerodynamic instability, and we have also seen that even though it is theoretically possible to operate on the positive slope of an axial compressor map, where operational stability can be maintained, it is aerodynamically not unstable. And there are different modes of aerodynamic instability. We have seen rotating stall and surge being the major modes of instability. Rotating stall obviously involves a set of stall, either one or more stall cells moving along the annulus of the compressor in a direction that is opposite to that of the rotor rotation, and rotating stall could be either part span or full span or deep stall. So, you could have either of these modes in rotating stall. Surge is an extreme instability which is encountered in an axial compressor, wherein the compressor operation, there is a complete breakdown of stable operation of the compressor, and it is a highly transient phenomenon where there is movement of mass flow along the length of the compressor back and forth, and it is axisymmetric. Rotating stall is not axisymmetric, whereas surge is axisymmetric. That means, the entire annulus will be undergoing this instability, whereas in rotating stall we have seen that it does not affect the entire annulus, it affects only part of the annulus, which is why rotating stall is not axisymmetric, surge is indeed axisymmetric. We have also seen that rotating stall can have very high frequencies of as high as 50% of the rotor frequency itself. Surge, on the other hand, is characterized by very low frequencies, usually one order of magnitude less than that of rotating stall. So, these are the different instability modes that kind of affect the performance of the compressor, and it is important for us to understand this, because this limit of operation of the compressor puts a limit on the operation of the whole engine itself, and engine operation obviously cannot take place at points which are beyond the stable operating limits of the compressor. And that is why we had I was emphasizing the importance of understanding these instabilities and stable operating modes of the compressor. So, in the next class, as I mentioned, we will take up instabilities, little more discussion on instabilities. We will talk about the effect of distortion on the performance or stability of the compressor. We will also spend some time on discussion on methods of controlling these instabilities, because obviously we would like to control instabilities. At the same time, we would also like to operate the compressor as close as possible to the highest efficiency point, which incidentally might lie very close to the surge line. And so, we would also like to explore mechanisms or methods by which these instabilities, if initiated, can be controlled, so that the range of operation of the compressor can be extended. So, we will take up some of these topics for discussion in the next lecture.